All right. First, we're going to do a second order. Last time we only did the first order example on the PowerPoint. So I'm going to write out a second order. I guess I kind of gave it away. I will show you how you would know that this is second order. All right, so calculate the half-life for the decomposition of NO2 at 330 degrees Celsius. Also note, they're always going to give you a temperature because they're going to give you a rate constant. And so that is only the rate constant at that temperature. So you can have the same reaction and they can give you two different rate constants because they've changed the temperature. That's the only reason why they're giving you the temperature. So when you're doing the decomposition at 330 degrees Celsius, your K value is 0.775, 1 over molarity times seconds. All right, so I already told you it was going to do a second order example. This is how you know it's second order, because of the units of K. If the units were 1 over seconds, then it would be first order. If it's 1 over molarity times second, then you have a second order reaction. All right, and then they also tell you that your initial concentration of NO2 is 0.00300 molar. All right, so I'm not going to be real strict on sig figs, but when they give you 3 sig figs for K and 3 sig figs for the concentration, I'm expecting your answer to be in 3 sig figs. All right, you don't have to go through all the calculations. If the problem gives you 3 and 3, then you should be given 3 sig figs for your answer. All right, so if you know there's your second order equation. So that is 1 over the concentration of A at time t is equal to KT plus 1 over the concentration of A initial. There's going to be 3 of those types of equations given. You have to know that the 1 over the concentration, that is the one for second order. The one that is the ln of A, that is the first order. And the one that is simply concentration of A, that is the 0 order. So you have to know what equations to use for the different orders. And so you know this one is second order because of the units for K. And so then you use your second order equations. The equations will not be labeled as first, second, and 0 order equations. You have to know which ones to use. All right, the half-life equations are also going to be given. You're also going to have 3 of those. You have to be able to pick out the second order half-life, which is 1 over the initial concentration of A times your K value. All right, so once you know it's second order, you should write down your second order equations so that you can start solving this problem. All right, so here's the question. The question is, calculate the half-life. That is what it said, right? Yeah, calculate the half-life. All right, so if you have the equation, this is a very, very simple question as long as you can use your calculator. Here's the formula for the half-life. They gave you the initial concentration. They gave you the K value, and you just push the buttons on your calculator and you have your answer. So very simple question if you know your equations and you know how to use your calculator. All right, so your initial concentration, 0.00300 molar. And your K value is 0.775, 1 over molarity times seconds. So this molarity will cancel this molarity. All right, so use parentheses if you need to. Make sure you don't mess this up because you're not using your calculator correctly. All right, so if you are able to push the buttons correctly on your calculator, you see that you're going to have units of seconds. So you have in the denominator 1 over second, you invert multiply. Your units for this is seconds. All right, and so you push the buttons on your calculator, and if you do that right, you will get 430 seconds. All right, so you can convert this. You don't have to convert this. If you divide it by 60 seconds in a minute, you have 7.17 minutes. If you have a multiple choice question, make sure you're looking at the units. All right, so it might have the answer as 430 minutes. And if you pick that one, that is the wrong answer. It is 430 seconds. And then there's another answer that's 7.17 minutes. That is your answer. So make sure you're aware of units. Always be very aware of your units. All right. All right, so now my next question is going to be, how long would it take for it to decrease, for the concentration of NO2 to decrease to 25% of its original? There's a couple of ways to do this, but I am going to always, if you have a percentage. All right, so you're starting at the initial, that is 100%. If you go down to 50%, that means that is a half-life. If you go down another 50%, that is 25%. All right, if you go down another 50%, now you're at 12.5%. If you go down another 6.25, okay, so you can keep going and going and going and going. If my question is 50%, I know that's half-life. If it's 25%, I know it's 2 half-lives. If it's 12.5%, I know it is 3 half-lives. If it is 6.25, then it is 4 half-lives. So if your question is one of these percentages, I always use the half-life. If it is not one of these percentages, we will show you how to do that as well. All right, we already did this half-life. We calculated that to be 430 seconds. All right, so now we need to know, to go from 50% to 25%, what is that amount of time? And then we simply add those times up. If you are first order, it never changes. It would be 430, 430, 430, 430. Every single time, it would be the same amount of time. This is not first order. Second order changes. All right, because the half-life equation is not only dependent on K, it is based on your initial concentration and K. All right, when we were at 100%, we had 0.00300. That was our initial concentration. So this is our NO2 concentration. After we did a half-life, what does that mean? That means that it decreased by a factor of 2. And so now our concentration is 0.00150 molar. And when we go down to 25%, that means we have to cut it in half again. That means we're going to be at 0.00075. And if we want 3 sig figs, put a 0. All right, so you just keep cutting the concentration in half. That's what a half-life is. You had your concentration, you cut it in half. How long did that take? For this question, 430 seconds. Then we're going to cut it in half again and see how much time that takes. All right, and now we see that when we're going from 50% down to 25%, our initial concentration is no longer 0.003. It is 0.0015. So now we're putting in 0.0015 when we're going from our 50% down to 25%. K is a constant. It's not going to change unless you change the temperature. And it is 0.775, 1 over molarity times seconds. So again, the molarities cancel. You have 1 over seconds in the denominator. Invert, multiply. Your units are seconds. And you get 860 seconds. All right? Because when you do half-life, it is going to double each time. All right? So for first order, it's the same. Every single time you would write whatever you got for the first half-life, it is exactly the same for every half-life. For second order, since we are taking each time 1/2 of our initial concentration, that is the 1/2 in the denominator. Invert and multiply. You're multiplying it each time by 2. So if we wanted to go down from 25 to 12.5, we don't have to put it into the equation. We can. If we put in the 0.000750 and K, we would get the same answer. But it is 1720. So times 2, 0, 1, 2, 7, yes. So I'm just trying to multiply it by 2. So that's how long it would take to go from 25 to 12.5. And to go from 12.5 to 6.25, that is 3440. So second order, the half-lives will double each time. Every time you go to the next half-life, it doubles that amount of time. All right, and so the question was how long to go down to 25%? Well, to go down to 50%, it took 430 seconds. To go from 50 to 25, it took 860 seconds. And so to go from 100% to 25%, we have to add those up. All right, and so we add our 430 seconds plus the 860 seconds, and we get 1,290 seconds. And so that would be the answer to that. Again, if you wanted to put that in minutes, it would be 21.5 minutes. All right, and you might get a different, there's always error in the last digit. If you get 21.4, 21.6, or 21.3, I know that you're doing it right. You're just doing it in a different method, and that is fine. All right, so now it can be calculate how long it takes to decrease to 10% of the initial concentration. All right, so now you cannot use the half-life method. 10% is not part of that. It's 50%, 25, 12.5, 6.25. What you can do, if it's multiple choice, is know that the time is going to be somewhere, when you add those up, we got to add up another 1720, but then even more than that. So we're at 29, so we're at 3,000 seconds, so it's going to be over 3,000 seconds, because if you add the first three numbers, you get about 3,000. But it's going to be less than adding another 3,000, so it's between 3,000 and 6,000. So you can look at this and get an estimation. If it's a multiple choice, maybe that's all you need to do. But if it's not multiple choice, you have to calculate it. And so this is how you're going to calculate that type of problem. Got to figure this out. Without this. All right. Here's the cursor. Got it. All right. So again, our initial concentration was given. It is 0.00300 molar. All right. And when we get to only 10% left, now we multiply it by 10%. All right. And we'll use 3 sig figs. Okay. So when it decreases to 10% of its original concentration, now we have our NO2 concentration at time t. It is only 10% of that. So we just move the decimal one spot. So now it's going to be at 0.000300. All right, so we had 0.003, now only 10% remains. And so we had to multiply that by the 10% of our initial concentration. And so again, now we have to use the other equation. So far we've only used the half-life equation. So now we have to use the 1 over the concentration of A at time t is equal to KT plus 1 over the concentration of A initial, our second order integrated rate law. All right, and now we just plug in our numbers. And again, once you have your concentrations, you will always have one unknown. In this case, it was how long. Our unknown is the time. So 1 over the 0.00300, our NO2 at time t. K is that's molar. K is 0.775, 1 over molarity times seconds. The time is what we don't know. That's what we're solving for. And our units, right here, the units are seconds. Our units that we're going to get for our answer is seconds. 1 over our initial concentration, which is 0.00300. All right, so again, you have a math issue. You have to make sure that you are going to, this is added to this side. Do not make simple math errors. These questions are hard enough to figure out what numbers to put in. You do not want to be making math errors. All right, so if we get our calculator and we take our 0.003 and we go 1 over x, that is 333.3 repeating. All right, so this is 333.3 repeating. Now, here, we're going to bring this to the other side. In order to bring it to the other side, this is an addition. We have to subtract 1 over 0.00300. We have to subtract 1 over 0.00300. And I think I put in the wrong number. That was the one I put in for this one. 0.003, right? So that is for the first one. All right, so now we put in the other one is 0.0003, 0.0003, and the 1 over x, and that is 3,300 repeating. All right, so we have our 1 over 0.00300 minus 1 over 0.00300, and that's equal to 0.775, 1 over molarity times seconds, and t. All right, so we have our numbers. For this one, it was on your calculator 3,333.3 repeating. This one on the calculator was 333.3 repeating, and that's equal to 0.775, 1 over molarity times second, and your T. Change to, okay. All right. All right, so we end up with, when you subtract out the 333 repeating, you have 3,000, and that is equal to 0.775. So, and that is 1 over molarity times second, and your T. So then you divide both sides by 0.775. Now it is a multiplying this number times T. To get rid of that, you have to divide. So remember, if you are adding, you have to subtract. If you're multiplying, you have to divide. If you are going to the other side, whatever you do to one side, you have to do the exact same thing to the other side. And so when we have 3,000 and we divide by 0.775, we get 3,870. We want 3 sig figs, so 3.871, no, 0, no, not a 0, we only have 3 sig figs, times 10 to the third. And then if we divide that by 60, now we would have it in minutes, which is 64.5 minutes. All right, so you would have the answer either in seconds or in minutes on your, if it was a multiple choice. If it's not multiple choice, then either answer is correct. All right, so when we estimated it up here, all right, the 10% was going to be to add these three. All right, so when we added these three up, to go from here down to here, we're at 12.5%. All right, but we're not going all the way down to 6.25%. When you add these three numbers, it comes up to about 3,000 seconds. All right, and so it's got to be more than 3,000 seconds, but we're not going to add the next 3,000 to it because it's not 6.25, it's in here somewhere. And so you know that the answer is somewhere between 3,000 and 6,440, and so that confirms our answer of 3,870. So if you want it out of scientific, that's 3,870. 3,870. So out of scientific notation, 3,870 seconds. So it is between, so we knew it was going to be between 3,000 and 6,440 seconds. All right, so it had to be somewhere between those two. By doing our half-lives, we could narrow it down. Again, if you have a multiple choice question and you know it's between these two numbers and there's only one answer between those, you don't have to do any calculations. But there's going to be many that are not multiple choice and you have to do the calculations. All right, so these are all second order. So second order are, they're the same as first order, except you have to know the rules. And the rules are, if you're doing half-lives for first order, they never change. If you're doing half-lives for second order, they double every time because they depend on the initial concentration. All right. so go here. All right, so reaction is believed to either be first or second order. It has a half-life of 20 seconds at the beginning of the reaction. All right, so the half-life is 20 seconds. But a half-life of 40 seconds sometimes later. All right, so your half-life changes. And this one changes by a factor of 2 as well. But any change, because your half-life for first order is exactly the same every single time. Any change in half-life eliminates first order. So the first order half-life never changes. And so since your half-life changes and it's either first or second, then it is definitely a second order. All right, so you need to know first order half-lives never change. Second order half-lives will double at each successive half-life. All right, so this week we're doing concentrations, we're changing them, and we're going to get our rate law. Next Thursday, we're changing the temperature, and we will get our different K values. Again, that's why the problem gives you a temperature, because the K value is at a certain temperature. All right, so here's the picture again where you have a room temperature reaction, same reaction going. One's at room temperature, one's boiling water. So we will do this next Thursday, although our water's not boiling, it's just hot water. They're boiling it fine. And you see that the hot one is going to react much faster. So the one at room temperature is still reacting. It's still purple. The one that was heated up is colorless, which was the indicator that the reaction has completed. And so you will find reactions go faster when you have a higher temperature. All right, so again, rate constant. That's again why they give you the temperature. So a rate constant depends on your temperature. All right, so it is a constant, and that can be confusing, but it's only a constant at a constant temperature. Once you change the temperature, you change your rate constant. So it depends strongly on your temperature. All right, so there is a collision theory. That means that the reactant molecules must collide with an energy greater than some minimum value, which is your energy of activation. And it also has to have the proper orientation. It has to collide at the right spots in order to get the reaction to go. And again, that energy is the activation energy. You will be required to write reaction profiles. All right, so the collision frequency, we're going to call that Z. F is the fractions of collisions with the minimum energy, and P is the orientation factor. All right, so these are the factors that go into your constant K. So again, if you increase the temperature, you're going to increase the speed of the molecules, and they're going to collide. And they're going to have higher energies. They're going to have enough energy. You're going to increase the K. So as you increase the temperature, your K value is also going to increase, which increases the rate of the reaction. All right. So here's just a slide showing that if you have the NO reacting with chlorine, if you have the correct orientation where the N is colliding with the Cl, you get a reaction. If you have the wrong orientation where the oxygen is coming in towards the Cl, you do not get a reaction. So the nitrogen comes in and you get your reaction, kicks out the chlorine. And then if you have the oxygen coming in first, that is the wrong orientation. The nitrogen is going to react with this chlorine and kick out this chlorine molecule. The oxygen will not. All right, so this is just showing you what it means to have the correct orientation. You have to have the right atom that hits the correct atom in order for the reaction to proceed. right, so now we're going to talk about your activated complex, which is the transition state. So you're going to have to write a reaction profile. All right, so energy, I always put potential energy on my y-axis, and then just simply time. All right, so you start here with reactants, and then there's some minimum energy, and then you get products. All right, and this is your transition state. All right, and then when you go from reactants to the transition state, that is called your energy of activation. When you have your energy difference between your products and reactants, that is your heat of reaction. That is your delta H, the difference in energy between your products and your reactants. In this case, my products are at a higher energy. Reactants are at a lower energy. So when I do that products, larger number, minus reactants, smaller number, in this profile, it is going to be positive, which means this is an endothermic reaction. So when you take your products minus reactants, you get a positive number, positive delta H. That's an endothermic reaction. All right. You can do another reaction profile. All right. So here are your reactants, here are your products, and here is your transition state. All right. The energy of activation is always going to be reactants to your transition state. Your heat of reaction is always products minus reactants. But now you see that products are a lower number, reactants are a higher number, and so in this case, your delta H is going to be negative. So this is an exothermic reaction profile. So you should be very familiar with both profiles, endothermic and exothermic reaction profiles. Progress of reaction, so this time or progress of reaction as it goes to the right. All right. Now, when we did our Hess's law, we know that if we reverse a reaction, the endothermic would become exothermic. All right. And so you can look at this as reversing a reaction. So a lot of times they'll ask for the energy of activation of the reverse reaction. The delta H of the reverse is simple. So if, let's say my delta H is for the first profile 60 kilojoules per mole. And let's say that my energy of activation is 120. All right, so that's my first profile. My second profile, we're not going to deal with right now. So that's my first profile. All right, so we know the energy of activation is bigger than the delta H. We can see that visually. That is a larger spot than this one. All right, and so I gave you the actual numbers. So when I took my products minus reactants and I got my delta H, it was 60. Energy of activation was calculated to be 120. So now the problem that they like to ask is, what is the energy of activation of the reverse reaction? So calculate, we'll do both, delta H and energy of activation for the reverse. All right, we've done the delta H. We know that when we reverse the reaction, we just change the sign. So your endothermic becomes exothermic, and it's exactly the same value. If you multiplied it through by 2, you'd have to multiply it through by 2, but we're just the reverse reaction, not multiplying it by any number. And so the delta H is very simple. It is negative 60 kilojoules per mole. In order to get the energy of activation, you actually have to look at the reaction profile. All right, so you have to go to your reaction profile and see that the numbers were given. This number from here to here was given. That number was 120. This number from here to here was given. It is 60. The energy of activation of reverse reaction When you're going reverse, now the products are now reactants going to the left instead of going to the right because we reversed it. What we're looking for, and I will put it in a dotted line here, when we're going reverse, that means our products are going back to reactants, and so it has to go over that energy hump. And so the question is, what is this energy hump? Well, we see that I just broke it right in half. It is 60, because a 60 and a 60 is a 120. So the energy of activation for the reverse reaction is a 60 kilojoules per mole. Energy of activation is always a positive number. Delta H is not. Delta H is positive if it's endothermic, it's negative if it's exothermic. Energy of activation is always positive. No such thing as a negative energy of activation. So you have to visually look at the problem to see it. If I want to do examples over here, let's say that over here I say my delta H is 40, negative 40 kilojoules per mole. And I say my energy of activation is equal to 60 kilojoules. All right, so what I'm saying is my energy, and so the question is, what is the reverse? So for the reverse reaction here, the delta H, it just changes sign. So if it's negative 40, I reverse it, now it's positive 40. So the question is, what is your energy of activation? How do you get the energy of activation of the reverse? You need to know what you're trying to find before you can get the answer. The energy of activation for the reverse, I'm drawing a dotted line for the energy of activation of reverse. It is from the products to the transition state. And so if you draw the reaction profile, you see that that is going to be your delta H right here, and your energy of activation. So in order to get the product up to the transition state, it is this value, which is 40, and this value, which is 60. And so my energy of activation is 100. All right, so you need to be able to draw a reaction profile. Then you can visually see what the question is asking. Because sometimes you've got to add them together. And to get your energy, sometimes you have to subtract them. You want to memorize when to add, when to subtract. I don't recommend that. I recommend drawing the reaction profile and visually seeing that I need this value. What they're asking for is this value right here. And so your energy of activation minus this delta H. If I need this large number here, that means I need my delta H and I need that energy of activation from the forward reaction. All right, so you will have to be able to draw a reaction profile and analyze the energy of activation. You have to label everything. Products, reactants, transition state, energy of activation, delta H. Those are the things, plus potential energy and time or progress of reaction for your axes. All right, now your transition state has what is called an activated complex. All right, so you have your reactants, you can draw your reactant structures, you have your products, you can draw your product structures. Now in the transition state, that is where it is transitioning from reactants to products. When you're at that transition state, you can go back to reactants or you can go forward to products. All right, so you're right at the top of that energy. You can continue or you can go back, and that is an equilibrium. As long as we have an equilibrium reaction, that's what it can do. All right. When we show the activated complex, we show it with a double dagger. So here is how we indicate that this is not a molecule that we're going to capture. This is not something you put in a bottle or a gas tank, or you cannot collect it. So NO is in a tank of gas, Cl is a tank of gas. You combine them and you get NOCl and Cl. You would never get NOCl2. This is your activated complex. And so once it's at the top, it can go forward and give you your products, or it can go back and give you your initial reactants. All right, so that's called a bar and a double dagger. And that is indicating that that is an activated complex. All right, and again, here's a reaction profile. So your activated complex is right there at the transition state. So your reactants were NO and Cl2. Your activated complex was NoCl2. Your products are NoCl plus Cl. All right, and so they give you the delta H. It's going to be endothermic, products minus reactants, that's 83. They give you your energy of activation of the forward. And so the question would be, except they answered it for you, what is the energy of activation for the reverse? So they're going to give you this number and they're going to give you this number. And they're going to say, what is the energy of activation of the reverse? If you draw it and show that this amount of energy is 83, and this amount of energy, your energy of activation from reactants to your transition state, is 85, you see that in order to get the reverse energy of activation, we need to know what this amount of energy is. And so you simply have to take your 85, subtract the 83, and see that that is your 2 kilojoules per mole. You do not have to draw these to scale because it is not drawn to scale. If this length is 2, then this length is nowhere near 83. It's like 2, 4, 6, 8, 10, maybe 12. So you don't draw them to scale, but you have to label your numbers. And if they ask for the delta H of the reverse reaction, that is simply negative 83 kilojoules per mole. All right, so the delta H is simple. Forward reaction is positive, then it's negative if you're going in the reverse. So that is just the same as we did for Hess's law when we reversed our reactions and we changed our sign of our delta H. So you will have to draw a reaction profile on the test. Make sure that you can recognize this as an endothermic reaction. All right, so the profile is endothermic. They also give you the delta H, which is positive, which is endothermic. And so you have to put the reactants at a lower value and a product at a higher value because delta H is products, a larger number, minus reactants, a smaller number, to give you a positive answer. It does not have to be drawn to scale. This one's not drawn to scale. None of them are going to be drawn to scale, but they have to show an endothermic profile and the numbers listed. All right, so here, so again, if it is this could be the question, and the answers are all there, maybe not. So the question here could be, where is the transition state? And you have to know that this is the transition state. And if I have it labeled as reactants and products, I won't ask that. Which ones are the reactants? Well, you need to know A and B are the reactants. Which ones are the products? C and D are the products. If this is on there, I'm not going to label it as reactants and products. Is this an endothermic or exothermic reaction? So you need to know that this is an exothermic reaction profile. If you don't see that, you know to find delta H. It is products minus reactants, and you can see that the products are a smaller number. It's lower on this scale, and the reactants are a bigger number. It is higher on this scale, and so that's going to give you a negative delta H, which is exothermic. All right, and so if it says label the energy of activation of the forward reaction, they have it labeled for you. I normally label it in here. All right, so that's your energy of activation. That's exactly what they have, but they have it written over here. Your delta H, and then I would always put the delta H here. Simply products minus reactants. And so if I wanted the energy of activation of reverse, then I would draw a dotted line. I'm looking for the energy that goes from the products to the transition state. And so I can visually see I need to add my energy of activation with my delta H in order to get that energy of activation for the reverse. And so that is your delta H plus energy of activation forward. All right, so, and that's what you're going to do for every exothermic reaction. You're going to add up the delta H and the energy of activation for the forward reaction, but you should visually show it so that you don't get that confused. And it's going to be part of the question to show the reaction profile. All right, so the Arrhenius equation you're going to have your K, which is a rate constant. You're going to have A, which is your frequency factor. All right, so it's a collision frequency. It's a frequency factor. And then E is your base of Ln. All right, so that's a button on your calculator. That is not a constant. Well, it is a constant, but it's not. You don't need it written down anywhere. It's on every scientific calculator. That is the base for Ln. EA is, of course, your energy of activation. R is the gas constant. Now, since your energy of activation is going to be in joules per mole, then the R value must also be in joules per mole, and that's why it is the 8.314 joules per mole Kelvin. And temperature, if you have just T, there is a 100% chance that it has to be in Kelvin. All right, so if you have a T, it's always in Kelvin. If you have a delta T, you can use Celsius or Kelvin. But if it is just T, it must always be in Kelvin in any formula, because you could never divide by zero if you try to divide by zero, because you can get 0 degrees Celsius, 0 Kelvin is absolute zero, nothing exists. And so your T is always in Kelvin. All right, so that form of the equation is not used very often. We're going to use it in the lab. We are not going to use it for the test. The equation right here is the one that we're going to use in asking questions on the test. All right, so this one relates your K constant, your rate law constant, to the temperature. All right, energy of activation is always a positive number. R, you have to know that energy of activation is in joules per mole. So R has to be also in joules per mole. So energy of activation must be in joules per mole, because R is 8.314 joules per mole Kelvin. And your T's must be in Kelvin. All right. Now, all I can say about the units for K is they have to be the same. All right, so K units are the same. They can be half orders, quarter order, it doesn't make any difference. As long as you have the same reaction, and that reaction is not changing from second order to first order to 0 order to third order to 2.5 order or whatever. Orders do not have to be integers. Orders can be fractional. You don't have to worry about the units for K. You just need to know that they are exactly the same. So the problem has to give you one of those K values. Whatever the units are for that K value, that's the unit for the second K value. All right, so here is an example. All right, so the rate constant for the formation of hydrogen iodide from its elements is 2.27 times 10 to the minus 4 at 600 Kelvin. All right, they put it in Kelvin for you already. Most of your problems, it's going to be in Celsius, and you have to convert it to Kelvin. Do not forget that step. All right, and we change the temperature like we're going to do next Thursday. We're going to change the temperature, and we will find the new rate. And so this rate is 3.5 times 10 to the minus third at 650. So if you look at these two numbers, minus 4, minus 3, this is a much larger by almost a factor of 10, all right? Because when you increase the temperature, you're going to increase the rate of reaction. The concentrations are the same. We're only changing the temperature. That means we have increased our rate constant K. So anytime you increase the temperature, you're going to increase your rate constant K. All right, and so now we can calculate energy of activation. All right, so the ln of P2 over, not P, K2 over K1 is equal to energy of activation over R, 1 over T1 minus 1 over T2. All right, so here is your K1, here is your T1, here is your K2, here is your T2. and R is 8.314. All right, and so you have both your K's, both your T's, you have your R, you have one unknown. All of these can only have one unknown. We are solving for one thing. In this case, we're solving for energy of activation. All right, and so your energy of activation is going to stay the same. So when you have your reaction profile, the reaction profile, I don't know if this one's endothermic or exothermic or whatever, your reaction profile is not going to change. You're going to get reactions to go faster, but you are not going to change the reaction profile. You will change the reaction profile if you're adding a catalyst, because the catalyst simply lowers your energy of activation. But without adding a catalyst, the reaction profile looks exactly the same no matter what the temperature is. What does that mean? That means that your energy of activation is a constant at any temperature. All right, you're just going to have higher temperatures, and you're going to have more molecules with the correct energy to form your products. So now, again, you have to be able to use your calculator. So we simply just put in the numbers. So the ln, K2, 3.5 times 10 to the minus 3. K1, 2.27 times 10 to the minus 4 is equal to, we want to find energy of activation, R 8.314. 1 over T1, T1 is 600, T2, 650. All right, so if it's multiple choice and you're bad with your calculator, that is not good for you because it's either right or wrong, and if you push the buttons incorrectly, you get it wrong. If it is a show your work and you put in all your numbers and then you calculate it wrong, you will lose minimal points. All right, so let's see. All right, so then you do your division. When you divide those two numbers, you get your 1.3 times 10 to the first. When you push the ln of 1.3 times 10 to the first, you get 2.56. When you take your 1 over 600, subtract your 1 over 650, you get 1.28 times 10 to the minus 4. All right, and we are solving for energy of activation. So in order to get energy of activation by itself, you multiply both sides by the 8.314. They're not putting in the 4, which is fine, 8.31. And then we have to divide by the 1.28 times 10 to the minus 4. We have to divide both sides by 1.28 times 10 to the minus 4. Again, make sure that you're not missing these questions because of math problems. All right, so now you have to multiply your 2.56 by your 8.314, divide by the 1.28 times 10 to the minus 4, and then you get your energy of activation, which is 1.66 times 10 to the 5th joules per mole. Note that many times it will say convert, or if it's multiple choice, all the answers are in kilojoules per mole. So make sure that you can convert your kilojoules and to joules, so 10 to the 3rd joules. And so your answer in kilojoules would be 166 kilojoules. All right, so again, those are the kilojoules per mole. That is the same answer. But again, if it's multiple choice, they may have that in kilojoules per mole instead of joules per mole. But joules per mole is the units you get because that's the units for R. R is joules per mole. Energy of activation, when you get the units, will be joules per mole. When you're putting in an energy of activation, make sure you're putting it in joules per mole, because if they give you an energy of activation, it's normally given to you in kilojoules. So the key here, and you're not going to get hardly any partial credit if you don't put your temperature in Kelvin and you don't put your energy of activation in joules per mole, and you're not using the correct R value. R values, there's a bunch of R values. You have to use the one that is in joules per mole, the 8.314. So units are very important. If you're ignoring units, you're not going to get any points on these. Make sure you have the correct units, and if you mess up a calculation with the correct units, you're going to get a lot of partial credit. All right, so now we have our energy of activation. And then it says, what is the K value at 700 Kelvin? So what is my rate constant K at 700? One thing you can say, it's going to be larger than it was at 650. So it's going to be a larger number than 3.5 times 10 to the minus 3. As you increase the temperature, you increase your rate constant K. All right, so let's see which one they decide to use. So, okay, so you pick a set. So we had listed our K1. So again, we had the ln of K2 over K1 is equal to energy of activation over R, 1 over T1 minus 1 over T2. All right, so energy of activation is a constant. So we now are going to use this energy of activation. That's going to be plugged in here. R never changes. It's the 8.314, always joules per mole Kelvin. All right. Now we want to know what the K is. We want to find out what K is. All right, so that is what is unknown now, when our temperature of that is 700 Kelvin. All right, so then you have to plug in another point, and that point is K1, your 2.7 times 10 to the minus 4, and your T1, which was 600. All right, so now we know our energy of activation, and then we have to plug in our K1 and our T1. If you want to use the other set and put it in, you'll get exactly the same answer. But your K1 has to go with your T1. Your K2 has to go with your T2. Since this is another set, we should probably call this one 3 and T3. So it is a third set of data. So at this third temperature, I want to know my K value. And so you could put in here your K1 and your T1, or you could put in your K2 and your T2. And that answer would give you the exact same answer. All right, so when you plug in your, in this case, they went with the K1 and the T1, and then they're calling this T2. Probably should be calling it is the third set. So this would be then K2. Note, if when you get your answer for K2, a very common error is to just put the number. And what are the units? They are exactly the same as the units for K1. Whatever units they give for K1, that's going to be your units for K2. All right, and so when you put in your temperatures, all right, so you get all of your numbers to the right, and so to the right you end up with 4.77. So they're showing that right here. So you do your parentheses first, 1 over 600 minus 1 over 700. You get that answer, multiply it by your energy of activation that we solved for in part A, 1.66 times 10 to the 5th divided by 8.314, and your number is 4.77 on the right. So on the left, we have the ln of K2 over 2.7 times 10 to the minus 4. On the right, we have 4.77. Again, you have to know how to solve when you have an ln. ln is base e. So when we take the e to the x button on both sides, this side, it just gets rid of your ln, and you bring down your K2 divided by 2.7 times 10 to the minus 4. On the right, you have e to the 4.77. You push that on your calculator, and that gives you 1.2 times 10 to the second. Now we simply multiply both sides by the 2.7 times 10 to the minus 4, and we get our answer. And that is 3.2 times 10 to the minus 2. And so we had our three K values. K1 was at the lowest temperature. It was 2.7 times 10 to the minus 4. K2 was at a higher temperature. It was 3.2, or not sure exactly, times 10 to the minus 3. I know the exponent was minus 3. It was almost by a factor of 10. And now we increased it another 50 Kelvin. And it went up again almost by a factor of 10, or maybe exactly a factor of 10, of 3.2 times 10 to the minus 2. Was it 3.2? No, it's 3.5. 3.5 times 10 to the minus. So it was 2.7 times 10 to the minus 4. K2 was 3.5 times 10 to the minus 3, almost a factor of 10. And then K3 was 3.2 times 10 to the minus 2, another almost factor of 10. The key is your temperature increases, your K must also increase. If that is not the case, then you have some math error somewhere. All right, the last topic in chapter 13 is reaction mechanism. They save the best for last. All right, so in a reaction mechanism, you're going to have elementary reactions, and you're going to add them up in order to get an overall reaction. So anytime you see a sequence of reactions and then get an overall reaction, this is then a reaction mechanism. Each step, so it's going to be listed, say step 1, step 2, all right? So each step in a reaction mechanism, these are called elementary reactions, all right? This mechanism has been determined experimentally, and your elementary reactions will use the coefficients. The only time you can use the coefficients in a rate law is if it's in an elementary reaction, which is a step in a reaction mechanism, because the experimental data was already done. Those can be used as the coefficients, as the orders of each of those reactants. Only elementary reactions, which already has been proven by an experiment, can be you can use your coefficient numbers. Any other reaction that is not an elementary reaction, you have to go and do the experiment and do it. The elementary reactions, the experiment was already run, and it is the coefficients that we use for our exponents. All right, so we're going to have two things that are going to cancel out in our overall reaction. One is a reaction intermediate. What happens in a reaction intermediate is we make this compound and then we use it up, and it doesn't show up in the overall reaction. That is a reaction intermediate. A catalyst is something that we added, and then we produce it, and then it cancels out. All right, so they both cancel out and they don't show up. A catalyst is added, a reaction intermediate is formed and then used up. So you need to know the difference between a reaction mechanism, or a reaction intermediate, and a catalyst, and we will go through a bunch of examples for that. All right, so elementary reactions also are called their molecularity. So it is the number of molecules on the reactant side. So when you have step 1, step 2, step 3, you can then be asked, what is the molecularity of step 1? What's the molecularity of step 2? If there is one reactant, it is a unimolecular reaction, and these are only for elementary reactions. If there are two molecules reacting, you have a bimolecular reaction. And if there are three, you have a termolecular reaction. And that's as many as we will ever have. So it's one of these three. One molecule, unimolecular. Two molecules, bimolecular. Three molecules, termolecular. Those are the only choices for the molecularity of a elementary reaction, which is a step in a reaction mechanism. All right, so here is a mechanism. So normally they will write step 1, step 2, step 3. But if they're also labeling it as elementary reaction, and that is fine. Now here, I do believe they're trying to show this as a equilibrium, and then the computer program wouldn't let that be produced, and so that's why there's a little rectangle there. All right, so you have your 3 steps. So in step 1, we have one chlorine molecule going to 2 chlorine atoms. All right, and so this is a unimolecular reaction because there's one molecule. In the step 2 elementary reaction, you have one Cl and one CHCl3. So this is a bimolecular reaction. In step 3, we have one Cl and one CCl3. Again, a bimolecular. So your molecularity is either going to be unimolecular, bimolecular, termolecular. In this case, the first one is one molecule, unimolecular, and the other 2 are both 2 molecules. They're both bimolecular. All right, when you want the overall reaction, you simply add them up, just like we did when we did Hess's law. You're going to add up the 3 elementary reactions. All right, and so on the left here, we have a Cl and another Cl. We have 2 Cls, which will cancel these 2 Cls. So we subtract 2 Cls from both sides. Here we have a CCl3. Here we have a CCl3. We subtract a CCl3 from both sides. And so the overall reaction, you get what's left on the left, and you put what is left on the right, and you have your overall reaction. So they didn't leave room for me down there. So it's simply Cl2 reacts with CHCl3 to produce HCl and CCl4. All right, so that is the overall reaction. You simply add up your elementary reactions. All right, so that is your overall reaction. Now, what's going to be, so what we see is we had Cl that was in our reactions there, but it's not showing up in the overall reaction. So you're going to have to label what that is. Since we made the Cl, we didn't add the Cl atoms, we made the Cl atoms and then we used them up, we see that the Cl is a reaction intermediate. Also, what we canceled out on both sides was a CCl3. And so since we didn't add CCl3, we made it in step 2, used it up in step 3. So your CCl3 is also a reaction intermediate. All right, we didn't add either one. We made both of those and then we used them up. So they didn't show up in the overall reaction. All right, so you'll have to add it up, get the overall reaction, and you will have to label any reaction intermediates and any catalysts. Reactants are easy. The things on the left, those are your reactants. Products are easy. The things on the right, that's your products. Anything that showed up in the reaction mechanism that does not show up in the overall reaction, it's either a catalyst or a reaction intermediate, and you'll have to label them. All right, let's work. Well, let's see what we got. All right, so let's try this one. So here is a reaction mechanism. All right, so they will either say, here's the reaction mechanism, or they will say, it occurs following these elementary steps. Elementary steps are steps in a mechanism. All right, and so here is step 1, and here is step 2. All right, and so for step 1, they're saying that this is a rate constant for step 1, and K2 is the rate constant for step 2. So K1 is for step 1, K2 is for step 2. All right. Now they're telling you right here, this is very important, that this first step takes the longest. It is the slow step. And so the slow step is called the rate determining step. All right. And so that is going to tell you the rate of this reaction. These are elementary reactions. And so we know that we can write step 1 rate law. Rate is equal to K1. And then for elementary reactions, you can use the coefficients. NO2 raised to the first, because this is a 1, times F2 raised to the first, because again, this is a 1. You can only do this, I can't stress this enough, you can only do this when it is steps in a mechanism, when it is called an elementary reaction. All other reactions, you have to determine the rate law experimentally. This reaction mechanism was determined by experiment. They are elementary reactions. That means that you use the coefficients as the order. And so it is first order with respect to NO2, it is first order with respect to F2, and it is second order overall. All right, so when we go to add these up, we see that the F atom and the F atom will cancel out. And so you end up with 2 NO2s on the left with 1 F2 yielding 2 NO2Fs. All right, so that is your overall reaction. All right, so since they tell you that this is the slow step, this is the rate determining step, this is actually the rate law for the entire reaction. And so your rate for the overall reaction, rate is equal to K, the concentration of NO2 to the first, don't have to put the 1, F2 to the first, don't have to put the 1. So when you are adding up your reactions and your first step is your slow step, that's what you want. In a rate law, you can only have your products, reactants, products, and catalysts. You cannot have a reaction intermediate in your rate law. As long as NO2 and F2 are not going to be your reaction intermediates, then you have a correct rate law. So we will go through a lot more reaction mechanisms next time. Homework is on Moodle. I have it listed, the ones that are in the book. For the ones in the book, I'm not going to be very strict on the due dates, except for if it's not turned in before you take your test, you're not going to get any credit. But ALV2, stick with the due dates on those. I do want you to keep up with things. You shouldn't be doing all your homework the night before the test. So tomorrow we have lab. We will meet in the lab tomorrow. No, everybody has a lab on Thursday. So everybody, there's 3 sections this year.